Okay, I think the recording has started.
Yeah, hi, I'm Davidson. So I'm working in the Total Compute Solutions team in the CUSS team. So this presentation is about how we have designed the firmware update to be happening in the Total Compute platform. I believe there was one more session which was given previously in the same platform about the firmware update spec. um, that was given by Manish, I believe, 1 year back. So this is about how that particular spec has been implemented um, in a platform. So the agenda is first I'll just give a brief overview of how the total computer software stack is, what are the different components that we have, and uh, and also I'll touch upon. I'll not go into detail about the firmware update spec here. I'll just touch upon the different terminologies that we have and some important concepts. And also, we in the total compute platform, I mean, the firmware update also makes use of the update capsule runtime service from the UEFI. I'll talk about that as well, and the overall call flow of how the firmware update happens right from the beginning till the end, and the things that has to be done after. Yeah. So this is the total compute software stack that we have. So um, we have the Linux kernel and EL0. We have the Android or the Pookie that's missed here. So apart from that, so we have a Linux kernel and U-boot in the normal world, and we have an EL3 secure monitor, uh, which is running in the EL3. And in the secure world, we have a Hafnium, which executes at SEL2, which does the role of secure partition manager. And we also have some secure partitions running on EL0. So this is the different components that currently we have in the total compute platform, right? So in this, we are going to make some changes to make the firmware update to work. So just giving a brief overview about the FFA, because I have mentioned about the FFA here and the SPMC and SPMD. You might be aware. Anyway, I'll just say a few words about that. So FFA is a framework where we have the different components. They interact with each other. So in the FFA framework world, we have components called the hypervisor, virtual machines, secure partition manager, secure partitions, right? So whatever, so we have so the hypervisor in the secure world is called a secure partition manager, and the virtual machines in the secure world is called a secure partitions. So the just like how the hypervisor manages a different virtual machine in the normal world, so the role of the secure partition manager is to manage the different secure partitions, and the secure partitions will have some information about. I mean, the secure partition manager will have some information about the secure partitions by using a manifest file. So there will be a different manifest file for each of the secure partitions, and all these components, they communicate over the FFA interfaces, right? So we have different FFA interfaces over here. So there are multiple messages within each section that I have described here, like how to find what are the different components that are currently running in the platform, and what is the task to be scheduled, and who is going to schedule it, how are we going to schedule it. So all this information can be also set from the scheduling interfaces and messaging interfaces to communicate between the different components. and memory management to share or release a memory, how it can be shared, and different attributes for sharing a memory. And so all these things, so we have a separate firmware framework specification. So uh, yeah, and we also have a firmware update specification that we have. So in the uh, firmware, I mean, I'm not going to into the detail of this spec, but just giving an overall idea and the different terminologies. So in the firmware update spec, so we have the model based on banks. So we have, so the platform can have multiple banks. When I say banks, it is like, so two different partitions for a same firmware. Like assuming if we have a boot image like boot A, boot B, kind of. So we can have multiple, according to the spec, we can have a single bank also, or we can have multiple banks for the same firmware. But in our total compute platform, we have followed a two bank architecture, where for a single firmware we'll have two separate copies. And image directory is yet again one more terminology. I'll explain about the image directory later. So staging area is nothing but where we'll have a temporary buffer of secure buffer in the uh, where we store the firmwares before we are writing to the flash. And states, so the firmware update machine state. So there are three states that are involved. So one is the regular state, where all the firmware, whatever that has been are running, they are accepted images, and we know that those firmware, we have tested it and it's working fine. So that is the regular state. And before updating any firmware, so we will enter into a staging state. So once we enter into this staging state, then we will start the firmware update process. And once the firmware update process ends, so we go into the trial state. So this trial state is where we check the newly updated firmware images. And if we find that to be working fine, then we will update the to the regular state in the next boot. So these are all the I mean, the different states. And yes, and so image directory. So image directory is it again is a structure that is maintained within the firmware update, where it holds the different information from the uh, about the metadata partition. Okay, I'll explain about the metadata partition and I'll explain about the image directory over there. So the firmware that we are going to update in total compute platform is the FIP binary. And within the FIP in total compute, we have BL2 loader and SCP, RAM firmware, and all the BL31 component, Hafnium we have, and the secure partitions, and also U-boot. So all these images will be packed together into FIP in total compute. And um, so moving ahead, so when I say a firmware update is happening, so what we are doing is I'm not referring as a single component like any of the single component. I'm just mentioning about the FIP. So we are going, the FIP is called as the firmware here, right? So this is the format of the FIP, where there will be multiple images, one again, I mean, one after the other, and the information about the images will be mentioned here. So
Question.
Yes.
Hey, Varun here. So in the previous slide, you said that you're using FIP. So does it mean that any firmware update package that you expect has to be in the FIP format, or do you
No,
expect
it doesn't
the
have to be. So whatever that that is currently implemented in Total Compute, we take this FIP. It can be of any firmware, it can be of any format. It doesn't have to be in FIP. So whatever firmware that that has to be flashed for that particular device or the particular use case, then it can be of any format.
I see. Okay. Sorry, one more question. In the previous slide to this one, you were talking about these banks. So is there an expectation somewhere in the implementation that about the actual, physical memory where is going to reside? So for example, with banks, do you mean these are different DRAM banks or different memory regions, or during your
Sorry.
implementation?
So it is not DRAM or memory banks. Sorry for the confusion. So this, when I say banks, they are partitions. So they are in the storage medium. If you see here, so this is the FIP A is one partition and FIP B is yet again one more partition. So this is what I was mentioning as banks. So this is the partition, the different partitions that are present in the storage medium of our total compute, where we have the FIP. So this is NAR flash essentially. So we have like 64 MB of NAR flash in our total compute platform, where we used to have this different partitions.
Okay, thank you.
Yeah.
Davidson, I'm not sure. Maybe I missed it, or I don't know if everybody on the call is aware that what you're presenting here is a mixture of there's the firmware updates enablement that we have in TFA, and then the ARM Total Compute reference platform. That a lot of what you're showing here is your sort of platform usage of the firmware enablement that we have in TFA for a platform to do firmware update.
Yes. So this is just an example of how the firmware update spec that is really implemented in any platform, right? So we can take this as a reference, like how it has been implemented, and yeah. So this presentation is regarding that.
Yeah, sorry, I wasn't sure everyone on the call appreciated the difference between what's TFA and then what's a platform reference, and in particular the total compute platform. That's all.
Yes, because whatever the support that is required for the firmware update spec has been already implemented in TFA, but there are no real platforms making use of it. So I thought, since we are making use of whatever the feature that is implemented in TFA, yeah, so I'll explain about that, so that people can make use of it.
Yeah, thank you.
Yeah, so this is so we have a GPT partition layout here, and we have 4 partitions here. So so this is like the bank that I said, like 2 partitions that we have for FIP. So at a time, one of the partition will be active partition, the other will be the to be updated partition. And we also have a couple of partitions called metadata, and the content of the metadata is also mentioned in the spec. I'll go through that. So yeah, so even here for metadata, we have a couple of partitions. And the content of the metadata is, so it has the information about the different partitions that we have, and the images that are present in there. So so if we have to mention about what is the active partition from where from where it has to boot, so we have the TFA, while it's booting, it has to read the active index from here, and then it will choose the partition based on this. So Yeah, so for each image entries, it has the so when you say image entry, so this is the FIP that is mentioned here, like the FIP A and FIP B. So for each so this image entry is for the FIP, and the image type UID is what is really important, uh, because that is how we compare and find what is the image that needs to be updated. And for this image type UID, because I mean for this for FIP we have one image UID, image type UID, right? So and we also have image UID where the in FIP A to to denote the image that is present in the FIP A. So that is we have the image UID. So image A, FIP A will have one image UID and FIP B will have one more image UID. But both the FIP A and FIP B will have one common image type UID, right? So it also has an accepted field where based on this we will come to know whether the image that is present in that particular partition is tested to be working fine or not. So these are all the information that is present in the metadata partition, and uh, the uh, the firmware update. According to the firmware update, so there are two components. One is called a firmware update client, and the other one is called a firmware update agent. Uh, okay, so here if you see, so U-boot in the implementation that we have done in the total compute, U-boot is our update client, and we have one more secure partition that is running here, which will be the update agent. So what is an client and an agent is? So from the client we request the agent to perform the firmware update operation. So this firmware update secure partition actually uh, will will have the support for the NAR flash and the GPT drivers, and also it will read the metadata from the flash, and then it populates. The update agent will have a data structure called an image directory where the information from the metadata, it will be consolidated into a different structure for an easy use. So that is the image directory structure, right? So to make the firmware update work on the total compute platform, we have a new secure partition, that is a firmware update secure partition. And this firmware update secure partition is part of the project called the Trusted Services. So in tfa.org, so there are multiple projects like TFA and TFM, and so there is one more project called Trusted Services, and the support for the firmware update. This secure partition, the source code is present in the Trusted Services project, and the support for the U-boot client is part of the U-boot itself, right? And yeah, so from U-boot, um if we say, I mean, if we see in the U-boot, U-boot has support for the FFA driver because it has to communicate with the uh, with the with the firmware update secure partition, which communicates through the FFA. So the support for FFA is added in the uh, U-boot, and also we have decided to use the update capsule runtime service. So this is an UEFI update service, right? So this is also incompatible with the UEFI spec, uh, which has a runtime service called an update capsule. So to make the update capsule runtime service work with with our setup, so we need a new FMP driver as well. So um, I'll explain about the FMP driver and the update capsule service in the following slides. So according to the UEFI spec, so we have something called an ESRT, which is the EFI system resource table, where it maintains a structure that captures the information about the different firmware that are present in the system. So when I say FIP here, so FIP is actually a system firmware that is needed only for the for the system. So we similarly we may have different devices in our platform, and each devices may have its own firmware, and some of them can be updatable, and while some of them might not be. So whatever firmware that can be updatable, we can in EFI it maintains a table, and it has a different entry for each of the firmware that can be updatable. So all these images, they are all these firmwares, they are represented with their GUID. So this GUID is what I mentioned in the image type UID for in the previous table. So it's the same here. Okay. So since we have different firmwares here and different devices here to manage each device firmware, to write firmware to each device, so the mechanism will be different, and we might need different drivers uh, to actually update the firmware of each devices, right? So we have one common way of a class of drivers called firmware management protocol drivers. So this is also again part of the UEFI spec, where the role of the firmware management protocol drivers will be to be able to access the to be able to read and write to the device firmware, which is like the updating the device firmware of each of the devices, and also it will also help in updating the ESRT, right? So this ESRT to populate the ESRT, actually each of the FMP driver has to get the information from the respective devices, and it has to give the information to and all those information will be populated in this ESRT table. So the primary purpose is of the FMP drivers are to update the different device drivers, and also not exactly to update the different device firmware, and also to get information from the device firmware and populate as part of the ESRT tables. So here the each FMP driver has these functions to be implemented. Out of this, only two are actually mandatory, which is the get image info, which is to get the information of the firmware of the device, so that it can be used to populate the ESRT, and set image, in which case where we are going to write the firmware to that particular device, right? So and we also have to create something called a capsule. Since we are going to use the update capsule runtime service of the UEFI, so to make use of it, we have to create a capsule. So so this is the FIP binary that we have, and using a tool called generate capsule, which is present in EDK2, we have to give the input. So the input here is FIP tc.bin in my case, and I have to also give the image type UID. So what is the image type UID of the FIP? And also have to give the name of the capsule, and this tool will generate a capsule for me. So so it has multiple layers of wrappers around it, and each layer will be used by the different services that are in the U-boot. So the update capsule runtime service will first read the EFI capsule header, and the FMP drivers, as I have said. So and it will get the image type UID from this capsule header, and it will pass. And it will give this data to that particular FMP driver, so that can handle this capsule. So this is the idea about the capsule. So this is the overall overall way of how the update capsule works. So this is the UFA capsule, uh, and during the update capsule process, what it does is it parses the capsule and gets the image type UID, and it also requests the different FMP drivers, because at a time there can be multiple FMP drivers that can be present, and each FMP driver is responsible for a particular firmware, right? So the update capsule runtime service will iterate over all the FMP drivers that are currently registered, and it will get the image type and it will get the image type from that FMP, and it compares with the image type that is present from the capsule. And once it matches, it will ask that FMP driver to, it will call the set image of that FMP driver, so that it goes and writes that to the flash, right? And once that is done, so yeah, again the uh, updated information of this firmware will be again populated in the uh, ESRT table again, because anyway the updated firmware will have some modifications, so that has to be reflected back, right? So if we consider till here, so it is mostly how the UFI is handling the update. And what we have done is, okay, I'll come to that. So so till now I have explained about um, how the firmware update looks in U-boot in the normal world. And now let's come to the secure world. So this is the sorry, if there is any question, yeah, please. Okay, so I'll move ahead with the secure partition implementation. So yeah, so as I have mentioned, so in trustedfirmware.org, you can find a project called Trusted Services, which has actually support for multiple secure partitions. So if you remember in my previous slide, I have also mentioned about that secure partition called crypto. So that is again used for some of the cryptographic services, and it has the embed TLS library in it, and it performs some decrypting and encrypting. So there are some secure partitions that are available in the trusted services, and we have also added this firmware update support as part of the trusted services project. So this firmware update will be running as a secure partition in SCL0. So it has, so this firmware update secure partition will have all the, it is the implementation of the firmware update, ARM PSA firmware update specification. So it has support for the NOR flash driver, so that it can read and write to it to the NOR flash, and it also has support for the GPT drivers to get the information about the different partitions that are present in the flash. And also it has the FFA driver support to communicate with the different components that are present in the system to communicate with U-boot. And um, yeah, so it is the so it is called the firmware update agent. And so whatever the roles and responsibilities of a firmware update agent that is mentioned in the spec has to be done by this secure partition. So the firmware update secure partition has these APIs. Um, so yeah, um, the discover is I mean, so all these calls are should be coming from the update client to the update agent, and the update agent, the role of the update agent uh, is to provide the service for these calls, and the update client has to make these calls. So once so the discover call will be coming from the client to the agent, and so what it does is the update agent has to give some information about the general information about the service, like what are all the different functions that are supported, and what is the version. And so we have some version numbers also just in case to so if in any case the firmware update spec is incremented, then it that has to be compatible. The update client and the update agent has to be compatible with the particular version. So all this information about the update agent, it can be retrieved a part of the so that the update client will know about what is the update service, update agent that is running over there. And so before we start to update, we have to put the state, the firmware update state into the staging state. And so that's the purpose of the begin staging and end staging. So once the update is done, then we have to come out of the staging state. And for any reason, if we want to cancel the firmware update in the middle, then we can call the cancel staging, so that all the whatever work that was done before, it will be just flushed out, and it will not be it will not make any it will not be written into the flash. So uh, so so we have like open, read, and write. So the update client can actually use these APIs to. There are in open, it can open two type of files. So one is it can open the image directory, or it can open uh, the firmware that is managed by the firmware update secure partition. That is the image tab UID actually. So the image directory also has a unique UID, and the other firmware also has the image tab UID. So based on that, it will open whatever that the U-boot wants to open. And the read stream will be called whenever we are opening the image directory, because uh, the U-boot can come to know about the different firmwares that are over there using the read stream. And to update the firmware, we call the write stream. And the purpose of the write stream is to transfer the firmware from the normal world to the secure world. And in the secure world, we have a staging area, and the content of the firmware will be placed over there. And during the commit, whatever that we have in the secure memory, so that will be written to the flash. And accept image is to actually accept the image, like whatever the image that we are updating. uh, After running some acceptance test, then if we find that the image is good, then we can call this to make sure that the image is good. And select previous is just to uh, select the previous bank. Okay, so all this can be done using the if you look at the metadata that I have explained before, so that has a field called accept field. And also the select previous, so that also has fields like what is the current active index and what's the previous active index. So these calls will make changes to that to those fields in the metadata partition. Okay, so we have in the uh, so all these are part of the U-boot, and in U-boot we have the update capsule service. And as I have mentioned before, so it will call the get image info for populating the ESRT, and it will call the set image for updating the firmware. And these are all the calls that get image info will internally make use of it. So till here it is part of the UFA spec, and from here, so this is part of uh, the PSA firmware update spec. So this is just like the backend implementation for the firmware update of the UFA spec. So how the communication between the U-boot and the firmware update SP happens is, so the U-boot so whatever it will create a message, and it will So we have memory so that is shared between the U-boot and the firmware update secure partition. Yeah, so this can be done. I mean, so this is a carved out memory, and this memory cannot be used by the operating system or any other components. So the U-boot will make a message, and it will copy that message into this memory, and it will send the FFA direct message to the secure partition. So once the firmware update secure partition gets this message, then it will go and read the memory, go and read the message from this memory. So this is how the communication between the U-boot and the firmware update secure partition happens. And so we have different layers over here. So the client and the agent. So this communication is basically uh, the whatever the firmware update APIs that I have mentioned before, like the discover, open, read, write. So all these, so each message has its own. Some of the message has a payload, and some doesn't have. Like read and write message has a payload because it has to, whatever the content that it has to write, it copies it into the payload and it sends. And most of the messages have just a header. Like if we want to do the begin staging and end staging, it doesn't need any payload, so it will just have a header. And so this message will be useful and it will be used by the update agent and the update client. And in the RPC layer, so we have since we are using the UEFI services, so we also thought we'll go with the management mode, standalone management mode way of communicating. So that is nothing but we add one more header into I mean before the message. So this header has so this STMM way of communication is again is a different topic, but what it has, I mean, in simple terms, the header has a service UID, right? So in STMM way of working, so uh, so the firmware update secure partition, once it receives this message, so first it parses the header and it will find what service, to which service it has to forward this message. So there can be multiple STMM services that can be running, and this the UID in this header should point to the UID for the firmware update service. So even the firmware update service has its own UID, and if the UID of the in the header matches to the UID of the firmware update service, then it will pass this message to the firmware update service. But currently in our implementation, we just have only one service, which is the firmware update service. Maybe we can have multiple STMM services running in parallel in the same secure partition, or it can be in a different secure partition. And we also use the FFA messages, as I have mentioned before, the FFA direct message request and response messages that we are using. So during the boot, what happens is, so what we have done is the support for the update capsule runtime service already present in the U-boot, and there are a couple of FMP drivers also present. But to match our use case, so we have come up with a new FMP driver, and so the role of the FMP driver, as I said, so that has the support for the set image and get image info, and that FMP driver will make these calls. So this is the implementation of that FMP driver, and the get image info of that FMP driver will make these calls, and the set image of that FMP driver will make these PSA firmware update APIs. So during the boot of the U-boot, so we have to first register the FMP driver, and during the registration, it also checks. So there is a this firmware update API called discover, as I have explained before. So the secure partition will give the information about the services that it does and the version, and these kind of information can be received um, in the U-boot. And the next thing is the U-boot will be populating the ESRT once all the FMP drivers are registered. So it will go through all the FMP drivers that have been registered, and it will try to get the image information of all the FMP drivers from all the FMP drivers. So to get the image to get the information that is needed to populate the ESRT table, the FMP driver has to call the get image info. And the get image info, as I have explained before, so it opens the image directory. So the open of the image directory will give a file descriptor for that image directory, and then we use that file descriptor to read, and it gives the content of the image directory. Right, so this content will be again, so this is a structure, and the firmware management protocol has its own structure to has its own way of representing the images and firmwares, and it will be mapped, and then that information will be given to populate the ESRT. So this happens during the boot. And during the update, what we do is in total compute, how we are doing the update is, so first as I explained, so we have to create a capsule using the generate capsule tool of the EDK2, and then we have to place it in the memory. So this can be done in multiple ways, and how we are doing it right now in our platform is during the execution of the model, we so there is a parameter where we can mention what should be the content of the DDR, and in what location it has to be placed. So during the boot of our model itself, so we will place the capsule, and in the U-boot, we have to stop it in the U-boot prompt. So we have a U-boot command line application, and that command line application, we have to mention the um, uh, address in which we have loaded the capsule, and that application will invoke the service, the update capsule service. And once the update capsule service is invoked, it will parse the capsule, and it will get the image type UID from the capsule, and it will try to find what is the matching FMP driver for that particular image type UID. And once that FMP driver is located, then it will call the set image info of that particular FMP driver to update the firmware. And so once that is done, yeah, it updates the SRT. So this is in the view of the U-boot, and this is in the view of the UFA update capsule spec. And our implementation of the PSA firmware update spec comes into the set image of the FMP driver, right? So once the FMP set image is called, so again, as I have said before, so it does the begin staging, and it sets the state to staging, and it does the open, and this time it passes the image type UID of the firmware. So as I have said, the FIP has its own image type UID, so it will say I would like to open the um, partition, the FIP partition, and also the firmware update secure partition internally knows what is the current active partition, and also what is the partition it has to be update next. And yeah, so once the open is been received in the firmware update secure partition, so it will create a staging area for that particular partition, and the FD of the staging area will be returned. And after that, the FD will be used for all this communication like write and commit. And then the write is it will transfer the FIP image from the from wherever that we have loaded previously during the boot to a staging area that is created within the secure world. So this write can be multiple times based on the size of the capsule and I mean size of the FIP image and also the size of the shared buffer. If the shared buffer is good enough to accommodate the entire FIP image, then it's just like one time write. And so once the write is done and then we commit. So what commit does is this is the place where we actually write the firmware to the flash. And so there are two ways of accepting the image according to the spec, where the whatever the images that the ideal way should be like there should be some kind of acceptance test that should run after the reboot. Um, so so after a reboot, what happens is the system will boot from the newly updated images, but still the accepted will be, I mean, it is not accepted. So what it has to do is like in the normal world, then that there should be some kind of acceptance test that should be running to check if the updated firmware is as per the requirements, and then it has to accept. But in total compute, we don't do that. I mean, we don't have the acceptance test right now, so we just immediately accept the image after we write to the flash. And then so this is end staging, where the I mean we officially close the firmware update is done. Yeah, so this is in trusted firmware. In the next boot, I think Manish will take it from here.
Yeah, thanks, Davidson. So this particular slide I have presented last time for firmware update also in the TFA, what the things we have developed. So this is the same way is used by the total compute team also. So when the during the BL2 entry point, we call the function fw init. So fw init will basically load the firmware update metadata which has been written into the GPT partition, and we'll get all the FW metadata where exactly the active index, and we basically we are more concerning for the active index, uh, which is the particular index where the firmware update has been done. We do the sanity checking of that firmware update metadata and also do the CRC32 validation of that metadata. And once all these checks get passed, we'll go to set, we'll basically then go and load the images from that active images, from that active index into the RAM. So basically the firmware update set metadata, plat fw set metadata image source is the platform function has been developed for the platforms, which they can use it in order to set the image source of the fw metadata. And plat fw set image source, this function is developed in order to get the updated images basically. So these are very much platform specific APIs, and partners can use these APIs in order to set the metadata image source and set the firmware updated image sources. So as Davidson mentioned, we are using the FIP concept. So we are having only one image source over here, that is the FIP. So we are just setting that image source exactly where in the flash this FIP is located. And once we get that particular location, we just load the images from, load the FIP image from there, and then start extracting that FIP and getting all the images UID from there and load those images into the particular RAM location. Next slide, please. So in the once during this particular flow, we are also checking whether the system is running in the trial run or regular run. So if the system is running in the trial run, so trial run is one of the flag is mentioned in the firmware update metadata. So as Davidson mentioned, there is one accepted flag is present over there, which generally gets updated when we do all the sanity check, and then we make that flag as a true. But during the initial update, during the update happened, in the subsequent reboot, the system runs in the trial run, and that time we do not update the NV counter over there, platform NV counter. So this is to just avoid this is to just avoid, like, if this firmware update is not proper, then we should not make the device kind of unused if we update the NV counter unnecessarily. So this particular flow is already been developed. The patches are already been merged, and it is being used in the ARM platform. And I think these calls are also leveraged in the ST-Rickson platform also, and they are also using this particular call in order to make the firmware update using the normal world flow. I think they are not using this secure normal world secure world communication. I think their update agent and update client both are residing into the normal world only. But these calls are kind of very much available to every platform. Yeah. So yeah,
Okay.
again back to you. Yeah.
Yeah, Manish, thanks. And yeah, so moving ahead, the things that we are planning to be done in total computers. So currently we stop it in the U-boot prompt and then we update from U-boot. So moving ahead, we are planning to have an over-the-air update where there will be some kind of service running in the user space of the Linux, and it gets the firmware from cloud, and then we should be able to call the runtime service, uh, and we should be able to update the firmware. So that is in pipeline. And also so as if you have remember seeing the capsule, so there is some kind of an authentication info that is present within the capsule, which we are not currently using it, and we can use that also. And even the firmware update spec has a different way of authenticating the image, so that can be done in the firmware update secure partition using the root of trust keys. Yeah, so these are the ways in which we can ensure that a proper firmware is updated. And the firmware update spec also has some details regarding the anti-rollback counter, where it should not revert back to um, older versions of the firmware. Yeah, so as I have already explained, so there are no acceptance tests currently that we have in total compute, and all the images are are accepted immediately after we are writing to the flash. So that needs to be done. And there are also selecting a previous image. So there is a firmware update API, and that has to be used in a real use case, and that's again to be done. And also a recovery mode also has to be there. So these are the things that needs to be done. So currently whatever that we have done in the total compute is just the basic bare minimum firmware update, assuming that everything is fine, like we create, assuming that we update the proper firmware and everything works fine. But all these features and the security enhancements also needs to be done. And yeah, so for reference, so the firmware update spec, if we can get it from here, and the UFA spec has the information about the runtime services, and update capsule is one of the runtime service of the UFI, and it also has information about firmware management protocol, ESRT, and GPT partition layout. Yeah, so the trusted services project that hosts the firmware update, and most importantly, all this support, whatever that we have done in U-boot and trusted services, they are not yet in the public. So for our next release of the total platform, it will be released, but as part of form of patches. Um, anyway, I mean, we have plans to upstream it, and it will be done soon. Yes, so that's it. I'm sorry, I think it was a long presentation. Yeah, please, if there is any questions.
There are any questions, I'm happy to keep the call going to take them. Or if people have to drop off, you know, I'm sure we can take some questions on the mailing list. But if there are any live right now.
Yeah, just curious about the partition updates, wherein you're updating, let's say, EL3 or the half name image itself. So what kind of acceptance tests do you envision running on those? I mean, I'm just trying to wrap my head around the concept that you run the acceptance tests after they have been flashed and you boot up in this trial mode.
So we haven't thought about that yet, like what kind of acceptance test can we really have to cover all the components that are present in the FIP. That is going to be a real challenge. But we don't have any plans on that yet.
Okay. And does your update mechanism also handle scenarios where the image itself is higher or larger than the partition size available?
Yeah, so it the when the firmware update secure partition, actually it knows what is the size of the partition by reading the GPT headers, and when the incoming when the incoming image, it also checks the size of the incoming image, and it has a check over there.
So will it just bail out if it is a larger one, or will it go and
Yeah,
update
even
the?
before, yeah, it won't update. It will check and it will say that the size of the image is more than what it can accommodate within that partition.
I see. Okay.
Any more questions?
Oh, yeah, I have a very simple question. It looks like this is a very complete and complicated implementation of firmware update. So my question is this code has to be implemented, when it's manufactured, or can it be updated, before you don't have the firmware update capability, then you will run an application and then update this platform with all these features?
So whatever that we have currently done is it actually requires some sort of an yeah, till at least the support till the U-boot is already there. Only then we can able to update the firmware.
Okay, yeah, I think needed, when a system boot in U-boot or UEFI environment, you may not need, if you don't have these things, you should have a way to plug in these features. Otherwise it has to be shipped, during manufacture, right?
Yeah. Yeah, but yeah, as of now, we don't have that support now.
And I think you might be referring to the recovery mode, which allows you to provision the rest of the firmware. And Davidson did allude to the recovery mode, which is like a bailout mechanism that allows you to go and overwrite the entire firmware store. And I guess that this is what you'd use when you want to provision the full set of firmware images after manufacture.
Okay, thanks. Yeah, that's probably a solution.
So does this also mean if the SP itself needs to be updated, then it will be done as part of the recovery mode?
Yes.
Okay.
Any more questions? If not, thank you, Davidson, for your presentation, and Manish. It's good to see the sort of the fuller picture. You know, we do all these various specs and enablement in different pieces of firmware. It's good to see an example, you know, of it all plugged together. And thank you very much.
Yeah, thanks.
All right, I'll stop the recording, and the recording will be available on the trustedfirmware.org TFA Tech Forum site in a day or 2 or 3, depending on exactly when I get to it. If anybody has any sort of follow-up questions, and after thinking about things, we can always do that on the mailing list, and I'm sure Davidson and Manish would be happy to field any questions there.